working through the related rates section. This is example 7, and it is a ladder problem. This is kind of a traditional problem that you'll encounter in several calculus courses. In this case, I have a 10-foot ladder that's leaning against a house. The lower end of the ladder is going to be pulled away from the wall at a rate of 2 feet per second. And when the lower end of the ladder is 6 feet away from the house, part A says, how fast is the ladder sliding down the house? So if you can imagine, we've got this ladder being pulled away, you know, by this little goofball, and poor unsuspecting person at the top of the ladder, his ladder's going to shift, right? And it probably wouldn't look quite like that. It's going to shift and slide down the wall. So the question is, how fast is it sliding down the wall? And we can find that, okay? You can see that this forms a triangle. It is a right triangle, and we had a fixed segment here, so we can lock this fixed length in for the ladder of 10 feet. The other two are going to be variables. The lengths will be varying. So let's just call it y and let's call it x just to coordinate with the coordinate plane. And the lower end of the ladder is being pulled away from the wall at a rate of 2 feet per second. All right, so my dx, since that's the horizontal movement here, dx dt would be 2 feet per second. This will be a positive 2 because I'm lengthening x as it gets pulled away. When the lower end of the ladder is 6 feet away from the house, how fast is the ladder sliding down? The question is, how fast is it sliding down? So our dy dt, our vertical movement, will be so many feet per second. Do you think this should turn out to be positive or negative? If this is sliding down, would y become longer or shorter? Well, it looks like it's going to be shortening. So you know what? I'm just going to note that this better be negative. It better be a negative value when I finish. And if it is, that's going to be an indication that I've probably got things going in the right direction here. And then this when is always an important piece to note. When the ladder is 6 feet away from the house. So it's away from the house. This is talking about a horizontal position. So when x is 6, we want to know what dy dx is. And we can see it is a right triangle. So x squared plus my y squared equals z squared, but z is a fixed segment. So I'm going to put my 10 squared right there for the ladder length. And I've got 2 variables, which I'm okay with. That should be fine. It's when I get 3 variables that I start wondering if I should do some substituting. So let's go into the derivative step of this. 2x dx dt plus 2y dy dt equals the derivative of 100, and the derivative of constant is 0. Let's sort out. I'm checking back up here. You can't see my eyes, but they're looking up at dy dt, and I want to keep dy dt then right here. So I'm going to subtract over 2x dx dt, and that will result in a statement that goes 2y dy dt is equal to negative 2x dx dt. If we divide it by 2, we can get rid of our 2's. I still need to keep a negative there though. And now we can substitute. I know dx dt was 2 feet per second. So I'm going to have negative x times negative 2. And when x is 6, we can also plug that in. Negative 6. That's going to be positive. I like the signs of that. And then y. Okay, so what should I plug in for y? I don't have a y. I'm trying to find dy dt though, right? So let's divide both sides by y, and we've got everything kind of positioned to conclude here. Now, here's the situation. When this ladder is pulled 6 feet away from the house, what would y turn out to be? Our ladder is stuck at 10 feet. The ladder's not changing. So we can do Pythagorean theorem to solve this, right? So it's going to be 6 squared plus a y squared equals 10 squared, or y squared equals 100 minus 36, or y equals the square root of 64. Oh, surprise, surprise. It's an 8. Isn't that a Pythagorean triple? It is, isn't it? 6, 8 triangle, or 6, 8, 10 triangle. So now we're going to pull in, we've got our y figured out, so dy dt equals positive 12 divided by 8, which could reduce down, divide by 4, so a 3 over 2 feet per second. That is part A. Oh, I shoulda had dy dt being negative, huh? Why did that not work for me? I pause for a moment. You know where my mistake is? I put in a negative 2 for dx dt, right? And that should have been a positive 2 like we had noted in the very beginning. I'm not sure what I was thinking there, but that should have been positive. And now we pick up the negative, and now I'm much more satisfied with the dy dt being negative, as we suspected it should be. You know, that's why it's nice to think about what your answer should be, what's a reasonable answer, and I knew it should be getting less, so negative. All right, there's part A. Let's get into part B. How fast is the angle between the ground and the ladder changing? So, I'm just going to go ahead and hit clear on this and start kind of fresh with part B. Okay, so how fast is the angle changing between the ground and the ladder? So they specified for us that it was between the ground and the ladder, not the house and the ladder, right? Because I really have two choices for my angle. Either the house and the ladder, or the ground and the ladder, and they're talking ground. So I'm going to set this up as my theta, and that means I can kind of remove that angle. I don't have to think about that one so much. The ladder, once again, is a 10-foot ladder. Let's call our x and our y there. And how fast is the angle between the ground and the ladder changing? So remember we had dx dt was equal to 2 feet per second. We're still playing with that number. And then we want to find the theta dt when, we'll stick with the when x was 6 feet pulled away from the side of the house. So those pieces are still in play. That means I need an x and I need a theta. I need x and theta involved in my formula. And that means I want this segment and this involved. So I'm going to use a trig formula, and that trig formula is going to be adjacent side compared to hypotenuse side, and that would look like a cosine then. So cosine theta is equal to x over 10. Two variables, I like that. I can take the derivative of each side quite easily. No product rule, quotient rule, or anything like that. Derivative of cosine creates negative sine theta times d theta dt, because our variable is different than t. And then the derivative on this other side is going to be a 1/10. And the derivative of x will become dx dt. Now let's plug in what we know and see what we don't know. I want d theta dt, don't I? D theta dt will equal 1/10. We know dx dt, hey, it's positive 2. And I would divide by sine, wouldn't I? So I divide by this negative sine theta, which could be rewritten as what? A cosecant theta if you wanted to. Not necessary though. Okay, so the only thing I have yet to find is, what is sine theta? Back to our picture. So we have, I'm going to draw my own picture here. We had the 10-foot ladder. This is the when time frame, when we have 6 equals x, the ladder was 6 feet away, what would sine theta be? Well, right now, we also know then that this would be an 8-foot segment, wouldn't we? This would be 8 foot for y. Sine is opposite over hypotenuse. Sine is opposite over hypotenuse. Opposite is 8, hypotenuse is 10. So I could replace sine theta with its ratio of 8 over 10 there. And that will get us our d theta dt. And okay, so just a little bit of math here. D theta dt equals a 1/5. We flip her over. 8/10. Don't lose the negative. And 5 goes into 10 2 times. We get a negative 1/4 is our d theta dt. So the angle is changing at a rate of negative 1/4 radians per second. Very good. Because the angle is shrinking, right? Which is what the negative is indicating. As that ladder slides out, theta is going to get smaller than what it was in the beginning. Makes sense. I like it. All right, part C. How fast is the area of the triangle formed by the ladder and the ground changing? We can do an area problem. I'm going to clear my screen again. So the last portion here, part C, we're working with the area of a triangle. We still have many of the same conditions going on. We have the 10-foot ladder, the x, the y, and this is going to be when x is, when x is 6. We also know we've solved this before. Y is 8. And we want, we know dx dt, once again, it was 2, but it was positive. And d area is what we're after, d area dt, when x is 6, y is 8. Okay, so now I need to blend together. I need to blend a formula that involves x and area. And the fact that we have a triangle, right? Okay, area of a triangle. Area equals 1/2 base times height. In our case, that would be an x times a y. And I don't have a great substitution, do I? I could do Pythagorean theorem and solve for y, but that looks messier than just doing product rule. So for our derivative, we are set to go with product rule. So dA dt is equal to, I'm going to lump the 1/2 x together and the y as my second term. So derivative of the first would be 1/2 dx dt times our second plus derivative of the second, dy dt, multiplied by the first, 1/2 x. All right. dA dt is equal to 1/2 dx dt is a 2. Our y value is 8 on this when spot, right? And then I'd have a 1/2 x would be 6 when we're trying to find the changing area. And now here's the one little dilemma, dy dt. But do you recall we're going to borrow the answer from part A, because part A took place when x was 6, just the same as we are right now. So we can insert into our calculation here an 8 plus a 3 times, now I've got to look at my notes. What did we come out with? We had a negative 3 halves going on there. For part A for dy dt. Look back at your notes. All right, so that gives us an 8 plus negative 9 halves. 8 is like 16 halves, so we get an answer of 7 halves. Looks good to me. Oh, let's talk label on that. The label would be, the ADT would be feet squared per second, because we're talking area. So 7 halves here, or 3.5. All right, that was a good problem. I'm sorry it took 15 minutes, but it's got a lot going on. It's a very standard problem for any calculus course. Thank you. Watch the next video, please.